Okay, I spent a little bit of time talking about intermolecular forces. And intermolecular forces are forces that happen between molecules. We're not talking about things that are inside molecules, but we are talking about forces that work between molecules. All right? The first one I'm going to talk about is something called London forces. Another term for these are dispersion forces. Okay? If you think about any electron cloud, okay, we tend to think that the electron cloud is all one charge. It's all electrons, it's all flowing around in a sphere. Well, that's true, but it doesn't take into effect that there's timing involved with the sphere. Statistically averaged, yes, there is a universal negative charge around the outer shell, depending upon the atom that we're looking at. But at certain times, you're going to find transient charges. Like over here, sometimes they're going to have negative charges build up on one side just by timing. Okay, sometimes all those electrons are more on one side than the other. So these dispersion forces are temporary buildups and lackings in the sphere of any given atom that have positive and negative charges. If you generate one that's got an extra excess of electrons, it's going to have a temporary negative charge. If you have one that builds up a temporary lack of electrons, then you're going to have a positive charge. And these things happen all the time, but they're transient, right? It all depends on location of electrons. So like little point charges that appear all over the sphere of any given atom. So they're not very strong. All they're doing is just showing mild weakness in different locations of a sphere at any given time. And that being said, you might run into another atom, and that other atom may have transient positive charges on one side. So for a temporary, very small interaction, these things come by and they kind of stick together, and then they start flying apart. Okay? That stickiness that you get between those spheres because of that transient charging is called a dispersion force. All right? So when you have a lot of these, they tend to build up. But these are the basic forces that you get with anything in the universe. Okay? The larger the molecule, the bigger the surface area, the more you're going to experience this dispersion. So this is all surface area driven. There's no way to really generate more of a positive charge or more of a negative charge within something that's a completely nonpolar molecule. You're just relying completely upon the dispersion forces. Right? So surface area is going to drive this, because the more surface area, the more chance you have of running into something that is partially positive charge or partially negative charges for that very small instant. Okay? These are weak. Very weak. All right? Very weak interactions. But they are there. And we can measure them. Matter of fact, you look at a gecko. Geckos don't have claws to claw up walls. What they do have are millions of hairs on their paws, or claws, or feet, whatever they're called. And these geckos are going to crawl up a wall because those millions of hairs, when pressed against the wall, add enough surface area to stick to the wall to overcome gravity for that gecko. And then as it lifts its foot, it's able to pull all of those dispersion forces off and then go somewhere else. So the geckos can literally travel anywhere so long as there's a surface, right? All right, so dipole-dipole interactions. If I've got something that's a dipole, like if I look at water, for example, I know that water has a positive charge on one end and a negative charge on the other. And this is a partial negative and a partial positive charge. They're not full charges. Okay? If they're full charges, there'd be a stronger interaction. But they're not. They're partial charges. But if I get another water that's nearby, that's got one of these partial negative charges, what ends up happening is I have an interaction between that oxygen and that hydrogen. Okay? Good. If I have another water that's nearby, partial negative, this partial negative is also going to interact with the other partial positives that are nearby. And that's just going to build up to form these dipoles. Now, when I get a lot of these particular dipole-dipole interactions, I usually get a lot of stickiness. This is the reason things like methane, which has a similar molecular weight to water, Why that has such a low boiling point, because all it relies on is dispersion forces. Water, on the other hand, gets to play around with these dipole-dipole interactions. And anytime you have something that's electronegative, like an oxygen or nitrogen, sticking to a hydrogen, it's got a special name. And that special name is hydrogen bonding. And hydrogen bonding is why water is so special. Okay? It really drives a lot of the special properties that you get with water. So of all these interactions, it's one of the stronger ones. It's not as strong as ion dipole, but it is quite strong. Okay? So I'm going to call this one strong. The boiling point differences are quite extraordinary. If you look at methane, methane has a boiling point at, let's see, if I look at propane, which is heavier than methane, look at a boiling point of minus 42 degrees C. We all know water is 100 degrees C. Propane actually weighs more. So by rule, it should have a lower or a higher boiling point than water, but it doesn't. And the reason being is because water can have all of these dipole-dipole or hydrogen bonding interactions. Okay. Finally, I come over here, ion dipole. It's just what you think it is. If I've got something that's ionic, so if I have water, okay, I've got something that's ionic, like sodium. Sodium actually has a point charge. That means that it's actually got a positive charge on its surface. So, the partial negative is going to stick to the sodium. Because it's a full positive charge, it's going to stick a lot better. And hey, look over here in the back end. I can put that chlorine of salt right there. And guess what? That's a partial positive back here with the hydrogen, sticks to the chlorine, and you get a nice strong interaction. So this is the strongest interaction. But as we all know, with ions and dissolved ions, sometimes they're not there. Sometimes we do get a lot of them. So as a result, these are not as common as the dipole-dipole interactions. Okay? So remember all of this. It's important stuff. It shows up everywhere in organic chemistry, especially this one and that one.